Welcome to our first subtopic, uncertainty and error in measurement.
So it begins.
First, let's consider uncertainty in measurement. Now, if we're using a digital instrument, our uncertainty is equal to the smallest division on the instrument. For example, if we have a digital scale and we weigh something at 10.5 grams, that means the digital scale's smallest division is 1/10 of a gram, and that's our uncertainty. So we should write down in our lab books for the measurement 10.5 plus or minus 0.1 gram. If we have an analog instrument, the uncertainty is half of the smallest division. For example, this graduated cylinder is reading 10.4 milliliters, but the smallest scale on here is 0.2 milliliters, so our uncertainty is half that, 0.1 milliliters. And for our lab book, if we're doing this a lab, we'd write down 10.4 plus or minus 0.1 milliliters. When we think about error in chemistry, we need to consider two things: random uncertainties and systematic errors. Now, random uncertainties, by definition, have an equal probability of being too high or too low. That's why we call them random. On the other hand, systematic errors always err to one side or the other because they're the result of a bad process. Our own system is making the errors. There are many causes of random uncertainty, and they're all listed in your book, just like there are many examples of systematic errors. The most important takeaway thing about random uncertainties and systematic errors is that random uncertainties can be reduced by repeating the measurements, because the repetitions average out to be the more precise and accurate measurement. Whereas systematic errors are not reduced by repeating the experiments, you actually have to fix the error in your process or procedure. Significant figures in measurement. By convention, when scientists communicate their measurements to each other, they always include the first uncertain digit. So for a concrete example, back to our digital scale, which measured 10.5 grams, and our graduated cylinder, where we measured 10.4 milliliters. These both have three significant figures. There's more to say about significant figures. If we take a number, say 450,000, and write it in everyday notation, it's unclear exactly how many significant figures there are there. Do we mean exactly 450,000, no more, no less? Or do we mean about 450,000, give or take 100 or 10? Or if we use scientific notation, where we express it as some number multiplied by 10 to a power, then we know exactly how many significant figures there are. In this example, there are exactly 400,000 and another 50,000, and after that is insignificant, buried in the uncertainty. You can write the same value, 450,000, in different ways that all express a different number of significant figures, a higher degree of precision. This last example shows that there are exactly 450,000, give or take 10. Precision versus accuracy. This is best demonstrated using our archery skills. 준비, 시작! Ooh, not precise and not accurate. Let's try again. That's precise, but not accurate. Try again. That's better. It's accurate, but it's not precise. See how if we could average where all the arrows landed, it'd be about the dead center? That's what we mean by accurate, but they're spread around. It's not precise. Let's try one more time. Oh, very good. Precise and accurate. Maybe you're ready to hang with this guy. Now, your book also includes this lovely graph to illustrate precision versus accuracy, and I'd like you to think about how to explain it to me in class time. The end. Thank you.